Let's see what happens when I put a fraction value in for a. What if I have 1/2 as a value for a, and then I multiply that by 2 to the x power? Let's go ahead and make a table. You guys go ahead and put 0 and 1 in for x. Is that what you had for your 2 points? You put a 0 in, you get a half out. Put a 1 in, you get a 1 out. Okay. So having the a value at 1/2, it kind of slows down the growth. When we had a 3 in there, it made the growth happen a lot faster. It just, instead of multiplying by a 3, we're multiplying by a half, and then that just, it cuts it down, right? So it just slows it down a little bit. So that's the difference that a value makes. It's still growth. It's still positive growth. It just isn't growing quite as quickly because it is slowing it down by having that 1/2 in there. Does that make sense? All right, so what if I ask for what is the domain and what is the range? Now the domain, remember, is what am I allowed to put in for x? Am I allowed to put negative numbers in for x? Am I allowed to put 0 in for x? Am I allowed to put positive numbers in for x? Okay, so what's my domain? All real numbers, right? I can put whatever I want in for x. So I can write it like this, or I can use my notation that says I can go from negative infinity all the way to positive infinity. So that's my domain. Domain's what am I allowed to put in for x. I'm not limited, am I, on my domain? And in all exponential graphs, listen now, on all exponential functions, I am not limited on my domain. It will always be all real numbers. Does that make sense? I am always allowed to put whatever I want in for an exponent. I put negative numbers in, not positive numbers in, I put zeros in it. But what's different now is what my range is going to be. Will I ever have, in this example, a negative output? Will I ever have a 0 output? I'll never have an answer of 0 either, will I? My outputs will always be what? They'll always be positive. They'll always be something bigger than 0. So I can write it like this. I can write that my range will always be, my y values will always be bigger than 0. Or I could write it like this. I could use a parenthesis, not a bracket, because it's not inclusive of 0. I could say my values go not inclusive of 0, but all the way up to it, all the way to infinity. So there's my range. What about the equation of the asymptote? That's also a question I'm going to ask. What is the equation of the asymptote? Don't give me a number. Need an equation. We all can see that it's the x-axis. What is the equation of the x-axis? It's y is equal to 0, right? It's not x is equal to 0. X is equal to 0 is the y-axis. If you still get those mixed up, and everybody does, hey, quite frankly, I got it mixed up. I was in college. I was teaching like my freshman year, they throw you into go teach one lesson, just to kind of get your feet wet in the neighboring high school. And I went in there. I got that mixed up. I taught it incorrectly, man. The teacher got so upset with me. She's like, I cannot believe that you're in college and you just taught my children the wrong. I did. I screwed it up. I'll admit it. If you're still getting it mixed up, grab 2 points on that line. Write them out. Hey, that's the 0.20. That's the 0.40. What's the same? The y values, right? Both the y values are 0. That's the line y is equal to 0. That's what I had to do. You only make that mistake once in front of your cooperating teacher. You do that wrong in front of a class of 30 kids, 30 freshmen, yeah, it won't make that mistake again. All right, so that's the line y is equal to 0. So those are the things that we're going to ask you to do. Domain, range, and asymptote. You with me on that? Okay, so before we do anything more with those, what I'd like you to do is turn to page 469. Okay, 469, and I'd like us to look at problems 19 to 24. They're matching. And I just want to see if you can match the equation with the correct graph. Okay? 19 to 24, matching. All right, so what happens when the b value isn't growing? What happens when the b value is smaller? So in this case, we're going to have a value just 1. We're just going to focus on the b this time. Remember, b is never negative. So we're going to talk about a b value that is maybe in between 0 and 1. So some type of a fraction or a decimal value, right? So it's not as big as 1, but it's definitely bigger than 0. So something like a half or a third. It could be 5/8, right? It could be 0.9. It could be 0.0001. But it just has to be between 0 and 1. So I'm just going to, we'll make it easy. We'll do 1/2 to the x power. So when this happens, that growth rate, it's not growing, is it? It's not getting any bigger. In fact, it's showing that it's getting smaller. When this happens, this is called a decay function. We're still going to call that a growth rate. It's just that it's growing in a way that it's making it smaller. It's shrinking. And this is what happens when they do those science problems, when they're talking about how much carbon is left, when they do carbon dating. This is the type of relationship they're talking about. They're saying how much has been decayed. Okay, radioactive decaying, when they're talking about that as well. Radioactive materials, they're talking about how much that decays over time. Same type of relationship. Okay, so a decay function. This means it loses half of its amount, or half of its reaction, or whatever the relationship is, for each amount of time that they're talking about. It might be a year, might be a day, whatever unit of measurement they're using, they lose half of that every time. So if you keep losing half, and then you have half left over, right? And then the next unit of time you lose half of that, you still always have something left over, don't you? And you lose half of that, you still have something left over, and you lose half of that, and you still have something left over. Will you ever have nothing? Won't you always have half? It might get really, really small, but you'll always have something. So in a decay situation, it's similar to a growth, but it's just getting smaller and smaller and smaller. It's getting closer to the x-axis, not further away. So as you continually lose half, right, it gets smaller and smaller. And so the asymptote is still going to be your x-axis, but it starts off big and then gets small and small and small. Let's make up our xy table here. My recommendation for decay functions is that instead of using 0 and 1, it's actually easier, much easier for you to use -1 and 0. Why -1? Well, when you take a fraction like 1/2 to the -1 power, do you get a fraction anymore? No, because what do negative fractions do? It flips it, doesn't it? So it's a reciprocal. Because it says I'm in the wrong location, right? Because both the 1 and the 2 are being taken to the -1 power. So the 2's in the wrong spot and the 1's in the wrong spot. So 1/2 to the -1 power is really 2. You with me on that? Use the calculator. That's fine as well. Just make sure you use parentheses around your 1/2. Okay. So if I put a -1 in place of the x, I get a 2 out. 0 is obviously easy because anything to the 0 power is 1. So now when I plot these 2 points, I get -1, 2, 0, 1. And I think you see what's happening here. I get this shape. I still have an asymptote, a boundary line. It's never, ever, ever going to cross. And this is a positive decay. It's positive decay because our A value, although we don't see it, we understand that our A value is a 1. Even if we don't write it up there, we understand that A value is 1. There's always an A value. B value here is 1/2. The B value is what makes it decay. Since the B value is something smaller than 1, it's between 0 and 1, makes it decay, and our A value is positive, so it's positive decay. Now what if I made that a -1? What if I wanted to graph f of x is equal to -1, 1/2 to the x power? Our xy table would be very similar, right? Wouldn't it just change our outputs by changing its sign? Wouldn't that be the only change? So I'd have -2, -1. Again, it's a reflection. That A value, if it's negative, it shows a reflection. So it would look like this. So yes, it's possible to have a negative decay. And that is when A is negative, just like the other, when we did growth. All right, so A determines positive or negative. You with me on that? I don't care if A is a fraction or if it's a whole number or an integer. That does not determine anything. You with me on that? The only thing we're checking on the A, is it a positive or a negative? Write that somewhere in your notes. The only thing that we're looking for on the A value is if it's positive or negative. It can be a fraction, it can be a whole number, that's fine. But we're just checking to see is it positive or negative. The B value is what we're looking for to decide if it is growth or decay. The b value decides growth or decay. If the b value is bigger than 1, then it's growth. If the b value is between 0 and 1, it's decay. And that's how that works. Just curious, are there some fractions that are bigger than 1? Are there any fractions bigger than 1? Are there any fractions bigger than 1? Yeah, improper fractions, right? So just because the b value happens to be a fraction, don't automatically assume it's decay, because maybe that fraction is improper. So check that out. Okay. All right, you will have you have got a worksheet for homework, okay?